Welcome physics students to another video on the photoelectric effect. In this video we'll be focusing specifically on energy considerations. So you have on screen at the moment an example of a metal with 1, 2, 3 different wavelengths of light. In the example of the 700 nanometer wavelength light, we find no photoelectron is emitted. In the example of the 550 nanometer light, we find that a photoelectron is emitted and it's got a speed of nearly 3 by 10 to the 5 meters per second. In the example of the violet, the 400 nanometer light, we find that a photoelectron has been emitted with a speed of over 6 by 10 to the 5 meters per second. So let's have a look at this and see what's happening in terms of energy. Photoelectric effect is to do with the energy being exchanged from light to a surface electron to release it. So in comes the instant light, it transfers its energy to the surface electron. It in turn shoots out as what we call a photoelectron. So at the start we have light energy, and we know some equations to work out the light energy. We can calculate the energy of light from the equation E equals hf, where h is Planck's constant, f is the frequency. We can derive a second equation, E equals hc over lambda, where c is the speed of light, 3.0 by 10 to the 8 meters per second, and lambda is the wavelength in meters. The work function is the energy required for the least bound electron to be released from the surface of the metal. And we can calculate that, sigma equals hf naught, and f naught is the threshold frequency. It's the minimum frequency of light required to release a surface electron. Now with any luck we've been able to release an electron and it's got some leftover energy which we find in the form of kinetic energy. So the maximum kinetic energy can be expressed by the traditional Newtonian physics equation, that being half mv squared, or in the photocell we can calculate it by multiplying the charge of the electron by the stopping potential, V naught. This is an energy sum. So the incoming instant light delivers energy to the electron. Part of it is used to release it from the metal surface, and what's left over is expressed as kinetic energy. So for example, if I had 10 electron volts, a unit that's commonly referred to with light, if I have 10 electron volts coming in from the light, and the work function of this particular metal is 4 electron volts, 6 electron volts is left over for kinetic energy. It's simple energy in, energy out sums. Another example, if I had 10 coming in again, the same light with the same wavelength or frequency, and this new metal surface has a work function of 2 electron volts, that means it'd give up 2 and there'd be 8 electron volts remaining for kinetic energy of the photoelectron. In my final example, if I had 4 electron volts coming in from the incident light, and the work function of this new piece of metal is 4 electron volts, that means it would give up all its energy just to release this electron from the metal surface. What would be left for kinetic energy? You got it, 0. In this case, we've just released the electron on the surface and no kinetic energy exists. This is a special case whereby the wavelength of this light is what we call the threshold frequency, just the bare minimum to release an electron without any gain in kinetic energy. Let's now look at the variations of how this equation can be expressed. Energy light equals work function plus the kinetic energy maximum. So we could use hf, our top left one here, for the energy of the light. Work function is the standard hf naught, and we could use half mv squared. So you could be asked to solve a question using this equation. You could be asked to calculate the frequency of the instant light, the threshold frequency, or the speed of the photoelectron. Alternatively, you could have the same starting point, E equals hf, the work function, and your kinetic energy could be expressed using ev naught. Another variation, we could substitute the hf with the hc on lambda, and that could be used as an expression to work out any one of these variables. And finally, we could do the same thing but use an ev naught for the maximum kinetic energy. So with these 4 equations, there are a large number of possible questions that examiners can ask students. Let's now have a look at these 3 different scenarios and see if we can work these out mathematically. So let's look at the red light first. We've got a wavelength of 700 nanometers, and task number 1, we're asked to calculate the energy of the photons in electron volts. So first of all, where possible, use electron volts in your calculation. So E equals question mark, lambda equals 700 nanometers, speed of light is 3.0 by 10 to the 8 meters per second, and Planck's constant, h, is 4.14 by 10 to the negative 15 electron volt seconds. Now we use the electron volt seconds version when we want to calculate a photon's energy into electron volts. So the equation we use is E equals hc on lambda to calculate the energy. We substitute our values in, and we find that the energy of this 700 nanometer red photon is 1.77 electron volts. Is this enough to emit a photoelectron? Clearly not. We see that the work function of this particular metal is 2 electron volts. So we need 2 electron volts to eject a photoelectron from potassium, and this photon of light is only giving us 1.77. So unfortunately, the energy supplied by the light is less than the work function, and the photocurrent is not emitted. Let's try the green light. The green light, same scenario, we're using electron volts where we can. Our wavelength is 550 nanometers. So we put that into the equation, E equals hc on lambda, and we discover that the energy of a green photon is 2.26 electron volts. Now, is a photoelectron emitted in this situation? Well, potassium requires a minimum of 2.0 electron volts, and this green photon is supplying 2.26 electron volts. So yes, it's greater than the work function, so a photoelectron will be emitted. Task 3, what's the electron's maximum kinetic energy? So we know that we have 2.26 electron volts coming in from the light, 2 being used up by the work function. So clearly, that would leave us with a leftover of 0.26 electron volts. We'd now like to work out what is this photoelectron's velocity. So we convert our 0.26 electron volts to an amount of energy in joules by multiplying it by 1.6 by 10 to the negative 19. That's the amount of joules that make up a single electron volt. So our EK max is half mv squared. Sub our values in, and we find the velocity of this particular photoelectron being stimulated by the green photon of 550 nanometers is 3 by 10 to the 5 meters per second. Let's repeat this process with the violet light. So E equals hc on lambda is our equation. We sub in our values. We do that and we find this particular wavelength of photon has 3.1 electron volts of energy. Is a photoelectron emitted? Clearly 3.1 is much greater than 2, and so it is. So yes, a photoelectron is emitted. So what's the photoelectron's maximum kinetic energy? So the difference between these two, the photon brings in 3.1 electron volts, and the work function requires 2. The leftover will be 1.1 electron volts of energy to be expressed as kinetic energy. Let's now work out the photon's velocity, or its speed. Again, we're finding speed in meters per second, so we're going to use joules in our calculation. So our 1.1 electron volts gets converted into joules, 1.8 by 10 to the negative 19 joules. We put it into our kinetic energy maximum equation, half mv squared, transpose, and we find this violet light produces a photoelectron with a speed of 6.3 by 10 to the 5 meters per second. And there's our summary. Let's now look at some sample questions. Scenario number 1, a photon of frequency 1.21 by 10 to the 15 Hz is shone on an unknown cathode. A photoelectron is emitted requiring a stopping voltage of 3 volts. What's the work function of the unknown metal? And what is the threshold frequency F0 of the unknown metal? So first of all, let's have a look at the work function. So here's all our variables. We know the frequency of the incident light. We know Planck's constant in electron volt seconds. And we know the stopping voltage is 3.0 volts. And we want to work out what is the work function. So where possible, let's use electron volts in our calculations. Now, interestingly enough, when we know the stopping voltage is 3 volts, that represents a maximum kinetic energy of 3 electron volts. It's one of the nifty little definitions. So by definition, a stopping voltage of 3 represents a maximum kinetic energy of 3 electron volts. Shortcut way to remember that one. Works for stopping voltage to energy in electron volts. So let's set up the appropriate equation. We've got HF equals phi, the work function, plus the maximum kinetic energy. Let's substitute our values in. So 4.14 by 10 to the negative 15 is Planck's constant in electron volt seconds, multiplied by the frequency of 1.21 by 10 to the 15 is equal to the work function plus the 3 electron volts that we worked out was the kinetic energy. When we do our sums, that produces a work function of 5 electron volts. Part 2, let's work out the threshold frequency. Listing our variables, the work function is 5 electron volts. We're after the threshold frequency, and we know Planck's constant in electron volt seconds. The equation we want is quite simply work function equals hf0, the threshold frequency. We sub in our values, and we end up with f0, a threshold frequency of 1.21 by 10 to the 15 Hz. So unless this light incident comes in with a frequency of at least 1.21 by 10 to the 15 Hz, this electron will not be ejected. Scenario 2, a photon is shone on an iron cathode, which has a work function of 4.50 electron volts. The emitted photoelectron has a speed of 9.38 by 10 to the 5 meters per second. What is the energy of the incident photon, and what is the frequency of the incident photon? So first of all, the energy. We're after the energy, we know its speed, we know its mass, the mass of an electron, and we know the work function. So In this case, again, we're trying to do a calculation using speed, so we have to use joules in calculations. So we convert our work function to joules simply by multiplying the electron volts by 1.6 by 10 to the negative 19. Let's pick our equation to work out the energy of this photon. So it's going to be equal to the work function plus the maximum kinetic energy. The work function in joules was 7.2 by 10 to the negative 19, and the kinetic energy is half the mass of an electron multiplied by its speed squared. We do all that work and we end up with the energy of the photon was 1.12 by 10 to the negative 18 joules. Now we want to convert that into the correct units because we're asked to calculate that in electron volts. We did it in joules because we needed to compensate for the fact we're working out kinetic energy with mass and speed. We divide the number of joules by 1.6 by 10 to the negative 19. That's the number of joules that make up 1 electron volt. And we end up with an energy of the incident photon being 7.0 electron volts. Question 2 of scenario 2, we want to calculate what's the frequency of the incident photon in hertz. Now again, where possible, let's use electron volts for our calculations. We already have the energy in electron volts, so let's use Planck's constant as the electron volt version. So we know that E equals hf. And from that, we can work out the frequency of light is equal to the energy divided by Planck's constant. So we sub those values in, and we get a frequency of the incident light of 1.69 by 10 to the 15 hertz. Scenario 3, a photon of wavelength 450 nanometers is shone on a sodium cathode, which has a work function of 2.28 electron volts. 2 questions: what is the maximum kinetic energy of the photoelectron, and what is the stopping voltage of the photocell? So question 1, it's maximum kinetic energy. Again, we try and use electron volts where we can. We have the wavelength of 450 nanometers. We have the speed of light as a constant. We have Planck's constant in electron volt seconds, and we have the work function as 2.28 electron volts. Hc, the energy of the incident light, is equal to the work function plus the maximum kinetic energy. Let's sub our values in. So there's our h value, there's our c value. Our wavelength is 450 nanometers, 10 to the negative 9, and that's going to be equal to 2.28 plus the kinetic energy max. So the maximum kinetic energy comes out to 0.48 electron volts. The next part of this problem, scenario 3, question 2, is working out the stopping voltage of the photocell. So we list our variables. We know the maximum kinetic energy is 0.48 electron volts, and we want to know what is the stopping voltage. Now, by definition, a photoelectron with a maximum kinetic energy of 0.48 electron volts will require a stopping voltage of 0.48. We did this type of example before where these two values are interchangeable in magnitude, but the units change. So the kinetic energy maximum, being 0.48 of electron volt, will require a stopping voltage of 0.48 volts. Had the maximum kinetic energy been stated in joules, then the following equation would be required. Final scenario, number 4. A photon is shone on a potassium cathode, which has a threshold frequency of 5.56 by 10 to the 14 hertz. The emitted photoelectron gains 2.0 electron volts of kinetic energy. 2 questions. First, what is the energy of the incident photon in electron volts? And second, what is the wavelength of the incident photon? So first of all, the energy. Let's list our variables. So we're after the energy. We know the threshold frequency, we know Planck's constant, and we know the maximum kinetic energy. Both these values in electron volts. Set up the appropriate equation. E, the energy of the incident light, is equal to hf, the work function, plus the maximum kinetic energy. Sub our values in. We do so, and we find the energy of the incident light to be 4.3 electron volts. Finally, question 2, what's the wavelength of the incident photon? Well, we know the energy is 4.3 electron volts, we know Planck's constant, we know the speed of light, and we want to work out the wavelength. And because the energy is in electron volts, we will use Planck's constant in the format of electron volt seconds. So let's select the appropriate equation, and it is E equals hc over lambda. We substitute and solve. We have 4.3 electron volts is equal to Planck's constant over the speed of light divided by the wavelength, which gives us a wavelength of 2.89 by 10 to the negative 7, or 289 nanometers. Thank you so much for watching this video. I hope these examples have helped explain the simplicity of energy in, energy out scenarios, energy sums of the photoelectric effect. If you've enjoyed these and learned something from it, please like, share, comment, and subscribe. And as always, thanks for watching.